Hi, everyone. Thank you for attending today's webcast. We are discussing multifamily hot water distribution systems. My name is Lois Arena. I'm the Director of Passive House Services here at Stephen Winter Associates. We are a consulting firm that deals with all the energy efficiency programs and all of the certifications that you can deal with out there on the market. My group deals specifically with passive house projects on large-scale multifamily buildings. So I'm really excited to hear about this session here today. We're going to start with just a few housekeeping announcements, and then we're going to move to our speakers, and then we'll have time for Q&A at the end. Please remember that your screen is customizable, utilizing all the various widgets found at the bottom. The presentations you can download them as PDFs from the resource list in the menu. So if you want to get those, please go there. You are in listen-only mode, but please put your questions in the Q&A box, and I'll be monitoring those, and we'll answer them at the end of the session. All presentations will be available for on-demand viewing within a few days of this hub, of the Engagement Hub. Zoom discussions will be open at the end of the webcast to continue the conversation and allow for additional questions. Please click the Zoom widget, which should be on your screen, or download the daily Zoom link PDF available on the Engagement Hub for the conference. Also, please be sure to complete the forum survey after your last webcast. It helps ACEEE in planning for future forums. Lastly, we want to thank all of our sponsors and partners for their support for the Hot Water Forum. And then finally, ACEEE would appreciate your feedback regarding this year's Hot Water Forum. You will have access to a survey link in all of this week's sessions on your console. Please take a moment after you've watched your last webcast and complete the survey. For those that do, you will actually get money. You'll get a $25 discount on your registration for the 2022 Hot Water Forum in Atlanta. So you get a little benefit there. Now I'd like to introduce our distinguished panel of speakers, please. We have Peter Skinner from E2G Solar LLC, Jack Aitchison from Associate for Energy Affordability, Eamon Delaga from PG&E, and Dr. Yanda Zhang from ZYD Energy Inc. Our first speaker today is Peter Skinner. He graduated from Lehigh University in 1970 with a Bachelor's of Arts and a Bachelor of Science in Civil Engineering, and holds an MS in Civil Engineering from Rensselaer Polytech Institute. Mr. Skinner established a multi-office science staff in the New York State Attorney General's Environmental Protection Bureau, guiding a team of scientists for 33 years. He founded and runs E2G Solar LLC, which designs, installs, researches, and teaches about residential and commercial solar thermal and heat pump systems, and with a particular focus on net zero multifamily projects, which is wonderful. He has authored 2 books, the latest being a solar textbook, Solar Hot Water Fundamentals is the title. He maintains a solar thermal instruction laboratory at SUNY Ulster and developed a line of solar teaching tools and curricula. He travels worldwide to undertake forensic investigations and design consultation and make presentations about advanced solar systems and plumbing engineering. He will be discussing hot water and thermal load measurements at Northeast multifamily buildings. Peter, please take it away.
Can you hear me here?
Yes.
That's great. All right, I want to thank you very much for that nice introduction. I'll be going through a number of slides here that describe the work that I've been doing in the last 2 or 3 years, not so much in the solar arena, which I still spend a lot of time on, but also in the plumbing area. The two are intertwined because solar feeds the plumbing system for hot water. So I want to first start with my first slide here and thank Gary Klein. Many of you know who he is. I was lucky enough to work with him actually out in California, where you can see that I'm actually getting involved with expanding PECs and working on his test apparatus that helps figure out what the pressure loss is in piping and in fittings. And I'm very indebted to all the mentoring he's given me. I'd like to just give you a little bit of information about what I'd like to cover. I started my designing work on plumbing systems with a clean slate. I didn't graduate as a mechanical engineer. I was a civil engineer, but with the same basic information and equations available to me as you would have as a mechanical engineer, I set out to design plumbing systems for the net zero buildings that I was involved with from a solar point of view. And in so doing, I started with a clean slate. But in so doing, I learned a lot, and that's how I met Gary, because Gary publishes a lot. And together, we've worked on a new approach that we like to call practically perfect plumbing, which reduces installation costs, saves water and energy, and gets the water to the tap fast. And that's what people want. But I did something a little different. I bought one of these Fluxus ultrasonic flow meters. Very, very accurate device. And I went around my projects and I started measuring the flows of hot water that were actually taking place. And I found very low flows, even at the 1 minute duration. And I started wondering why these pipes were so large. We have really gone forward, and I'll be talking about it as I go forward. The smaller pipes work better. Fat ones are passé. And we're moving forward now by demonstrating that with design, stress, and performance tests of what we do. And you're going to hear all about it. So let me just go right ahead because my time is short. The happiest clients are the ones whose installation costs are low. And they see their systems with low operation and maintenance costs. They like to make sure there's no tenant complaints and the water is really clean. Happy and safe tenants are happy tenants. They're happy because they get their water hot, they get it free of contaminants, it arrives quick, and it comes out with pressure, even when other people up the line are taking draws of their own. Now, we as plumbing designers want happy clients, that's for sure. We don't want any operation and maintenance embarrassments, and we certainly want safe water quality. What does the world want? Well, it wants reduced waste of water and reduced waste of energy. Is there anything else? I'm sure you can come up with a few others. But these expectations are risky, and people who do this for a living sometimes want to just oversize the pipes and sometimes complicate the networks so that pressure is there for everybody. We have designed systems that take this to a much smaller size pipe and still have the pressure and deliver the water quickly. The next slide shows one of our great adventures, and this occurred during lockdown. The experience that I had, I'm right now at Solara outside Schenectady. The room rings because it'll soon be occupied starting next week. I'm here to do some last minute adjustments of the plumbing system and the solar system before people move in. But I had some extra time, and Gary and I were talking, and we realized that Beacon Communities, which owns 20,000 apartments across 15 states, was building a second phase of the Meadows Senior Housing out near Utica. Well, I knew how much hot water the people were using because he already completed phase 1 buildings, and it wasn't very much water. And when I saw the plumbing inside that building, I just couldn't believe it. 3-inch pipe, 2.5-inch pipe. Why do they need pipe that big to take small amounts of water? So I wanted to make sure I wasn't wrong about this. Maybe I measured it wrong. So we bought a very expensive magic box from Hugh Henderson. Hugh Henderson is a metrologist. He's unbelievable. He's outside Syracuse, and he's retired. But I got him out of retirement long enough to build me a magic box, which has another great flow meter and a connection to his data cache and communication capability with all kinds of statistics and all kinds of stuff. Just great. And we started to monitor these buildings that Beacon owned, one of which was a Phase 1 Meadows building. And we were delighted to see that my original numbers weren't any different. We measured maximum hour levels for 35 apartments at 106 gallons. That's not a whole lot, let me tell you. And their maximum flow rate was around 1, maybe 2 gallons a minute for short durations. Now, you might want to know, why would you have a 2-inch pipe to carry that little bit of water? So, and my son helped me out with the statistics that I'm not as good with, the cumulative frequency. And you can see here that for Meadows, that at the 99 percentile level, the flow was 2.63 gallons a minute max. Now here at Solara, where I'm at right now, we have a more mixed occupancy, not all seniors, and we get something like 4 gallons a minute at the 99 percentile return frequency. So, you know, you've got to look at the building to make a good decision. So let me get back to Meadows. At Meadows, this was the Phase 1 design. If you look here, there's a couple of water heaters, goes into a 3-inch pipe, and then a 2.5-inch pipe, which leads to a 2-inch pipe that goes all the way across the ceiling of the 3rd floor. Then it, all the way along, it goes out on these branches that drop into downward risers, and then it returns to the recirculation. Recirculation, by the way, at 15 gallons a minute. And this is where you're getting flows of 2.63 gallons a minute max. So we knew that something had to change. And this is what we came up with. Simple, easy, and cheap to put in. This is an 1.25 inch line that goes out to a 1-inch line across the ceiling of the 1st floor with short branches, please, 1/2 inch, to manifolds, to the 2 adjacent rooms on the 1st floor and also on the 2nd floor, rises on a riser to the 2nd floor ceiling, 1-inch PEX all the way back to the last building, that's apartment 303, and then it goes on a 3/4 inch line back to the recirculation pump, which is very small. I'll talk about that in a minute. But this is a simplified loop, a little loop over here for 5 apartments above the tanks. When we talked to the plumber said, geez, I've been wondering why they've been using such big pipes. And so we had an ally there, and the owner was quite excited about making a change, even though the construction was underway. So this was a Hail Mary pass that Flutie would have been really proud of, trying to change horses midstream. So we looked at our layout versus theirs. We got rid of all the 3-inch, the 2.5 inch, the 2-inch, the 1.5 inch pipe. We cut back on the 1.25 inch pipe. We even cut back on the 1-inch pipe and cut back on the 3/4 pipe. And the only thing that we were a lot bigger was the 3/8-inch PEX home runs to fixtures. And yes, that was a lot of pipe, but it wasn't insulated, didn't have to be insulated. And overall, just for the pipe, we went from roughly $9,000 worth of pipe, $10,000 worth of pipe to $4,600. That's not even counting pipe insulation, fittings, labor, and equipment in the mechanical room, which we also made smaller. So it got put in. I went out and inspected the installation, and thank God I did, because I identified the fact that the plumber misread the plans and made one loop instead of a main one and a little one. Wow, it's good I caught that. I went out with a protocol and a whole lot of gauges that I calibrated to identify what the pressure change would be from the beginning in the mechanical room of the cold water all the way to the wand in apartment 303 at the end of the loop. And you'll see that, yes, there was a definite pressure reduction. But even up to 4 gallons a minute, which is much more than 2.63, we still had over 30 psi available to run the nozzle on the wand of the shower wand, that is, with the nozzle on it. Yes, there's a big drop between the trunk and that wand, but that's made up of the branch, the manifold, the twig, the valve, and the wand hose. That's a lot of little pipe to get through, and it still had 30 psi, more than 30 psi to run the nozzle, and it worked great. Then I wanted to check out something else. I wanted to make sure that our promises that people would get hot water quickly were met. And in fact, even for the first draw in the apartment, it arrived, warm water arrived in 10 seconds, and at 16 seconds we had 100 degrees, more than sufficient to wash your hands and even begin to take a shower in. Now, for the second draw at a sink or a shower or any other use in the apartment, we're talking 5 seconds. So it's that first one that's important indeed, and we were able to bring it in at a matter of seconds. There's another issue. These trunks, of course, act like radiators, and if you don't insulate them, you lose a lot of heat. Well, we noticed in the early phase 1 buildings, they were losing something like 180 million BTUs per year into the building. To me, that seemed like a lot of heat. The heat that was really going to waste in the summertime for sure, and the HVAC system had to take it back out. That was crazy. Gary then went ahead and calculated what would happen if that pipe had been insulated, because we guessed it wasn't insulated, and that reduces it to 63, almost a 2/3 reduction in the phase 1 buildings. But we wanted to know what our loop would do. So when I went out, I made sure that the insulation you see over here went everywhere, all the way right up to the manifolds that had the 3/8 inch home run PEX, 3/8 inch PEX to the fixtures. And just this was 3 weeks ago. I said, gee, I've really got to make sure that trunk line loss in our system was not a problem. And in fact, what we did was we were able to run 3 gallons a minute through the whole loop, and it approached 1.87 degrees. That's the difference between the mix out and the return temperature. That's the whole loop, including the recirc. And that's only less than 2 degree loss at 3 gallons a minute. When I did the math, that comes to about 28 million BTUs per year. Compare that, if you will, against 180 million BTUs per year. That's a reduction of about 85%. And you can't beat that. And so we feel very gratified with what we did. But, and the math is here if you want to download it. And we're happy to discuss this because we're really gratified with the results. Recirculation. If you look over here on the right, you'll see at Solara, where I'm at right now, I bought little pumps, little stainless pumps that pump about 2.7 gallons a minute. And it pumps out my loop in about 90 seconds. So after 90 seconds, I shut down the recirc pump and wait until the well-insulated line cools down to an appropriate number, and that's 30 minutes later, we turn it back on. That's not what's happening out at Meadows. These adjustable Loara circulators circulate very little water. In the main loop, like half a gallon a minute. In order to keep that water warm at apartment 303, this has to run almost continuously. So in short, that's a very different paradigm. I'm thinking about that as an option for the future. Love to have communication with you all about that. I just want to sum this all up. The plumbing revolution is here now. Gary talked about it, but he talked about a lot of things last week. I want to make sure you get it. you get it that smaller pipes are in, fat ones are out. Practically perfect plumbing can save energy, install costs, water, and get the hot water to the tap even faster. And you make tenants happy, and that's really the bottom line. We've made it work. Others can do it too. And Gary and I can help. I have here, oh, you can't see because I don't, oh, maybe you can, but anyway, here is plumbing engineering. Gary and I wrote stories about what we did, 7 of them actually, and we'll have an 8th coming out fairly soon about the experience at Meadows. It's in plumbing engineering in 2020, and you can read about it there. And you can also email me at e2g@verizon.net, and I'm happy to discuss this ad nauseum. That's what I do. I'm so proud of what Gary and I have been able to do, and he's done it nationally, and I've done it in New York. But bottom line is still, when you're done, make sure you inspect what the plumber is doing along the way, and then confirm the performance of the as-built system, and I can tell you how to do it. So I look forward to any questions you might have and visit with you in the Zoom section that follows. Thank you very much.
Thank you, Pete. That was excellent. For those of you that have questions for Pete, please put them in the chat. If you put his name first or whoever the speaker is that you're asking the question of, that would be really helpful at the end when we answer questions. Our next speaker is Jack Aitchison, an energy engineer at the Association for Energy Affordability in Emeryville, California. Jack has provided engineering and technical support for various comprehensive energy efficient decarbonization retrofits for multifamily buildings throughout California. He is always looking for new innovative technologies or strategies to conserve energy and reduce greenhouse gas emissions in multifamily buildings. Jack will take a look at recirculation pump controls and crossover issues for existing multifamily buildings, hidden challenges and solutions. It's great. Jack?
All right. Thank you, Lois. I will be presenting on recirculation pump controls and crossover issues for existing multifamily buildings, hidden challenges and solutions. So we'll be looking at 2 different recirculation pump control strategy types, demand controllers and variable speed recirculation pumps with temperature controls, looking at how they performed at saving energy in 5 multifamily buildings in California. So just a quick overview of a multifamily recirculation system. We have our recirculation pumps circulating hot water 24/7 throughout the building. Now, the idea here is that even the tenant furthest from the water heater will have hot water readily available in a timely manner. And like I said, that pump is typically running 24/7. So by adding controls to limit the runtime of that pump or limit the speed of that pump, we'll save pumping energy. But the focus of this presentation is going to be on the water heating energy it saves. So the lower speeds, the less time that pump is running, the less water that is returning into that water heater, and the less water that that water heater has to reheat and send back out into the loop. So the pump control strategy types we'll be looking at today are recirculation pump demand controllers. The recirculation pump demand controller connects to an existing recirculation pump. It has a flow meter that connects to the cold water makeup and a temperature sensor that connects to the return line, reading water temperature in the return. Now, this control strategy allows that loop temperature to fall below usable temp, typically below 105 degrees. And when that temperature is below that usable temp and there is a draw for hot water, the pump turns on. So it's a fairly aggressive control strategy type. The other control strategy type we'll be looking at are variable speed ECM pumps with temperature controls. This is a direct replacement for the existing pump, and how it works is it fluctuates speed based off return water temperature. So typically we set that pump to be about 20 degrees less than the supply temperature going out. And a pump that's continuously running, a single speed pump that's continuously running, we typically see return water temperatures around 5 degrees less than the supply. So it's a fairly large increase in the differential in temperature between the hot water supply going out and the return water coming back. So as I mentioned, we're going to be looking at 5 projects which installed either a demand controller or a variable speed recirculation pump and see how they actually performed at saving water heating energy. Now, these 5 projects, they all are central water heaters with, and those water heaters are gas. So we're going to be focusing on the gas common area meters. In blue is the projected variable speed recirculation pump savings, and in orange is the projected demand controller savings. Now, one caveat to these 5 projects is they all were enrolled in energy efficiency rebate programs in California. So in order to be eligible for those rebates, they had to do a pretty comprehensive scope of work. So we picked these 5 because we were best able to isolate the recirculation control savings from other measures that they completed. So starting with property number 1, this property installed a demand controller. It's a fairly large property. It has 80 units and 1 water heating plant with 1 recirculation pump. However, there were multiple risers and multiple recirculation loops. And the scope of work included demand controllers, low flow shower heads and aerators, as well as 1 central washing machine upgrade. Now, a quick note on that scope of work, the demand controller was the highest energy saver, or projected to be the highest energy saver of those other measures. So it should have the most influence on the savings. Now, the dashed line in the graph is predicted gas usage after construction, and the solid orange line is the actual gas usage post-construction. So as you can see, we are not seeing the savings that we anticipated for this project. Moving on to property number 2, this property was 34 units, 2 water heating plants, each with their own recirculation pumps, so a smaller recirculation system serving 17 units each. Similar scope of work to the previous project, demand controllers, low flow shower heads and aerators, 4 central washing machine upgrades, and pipe installation in the boiler room. Now, a fairly interesting event happened at this property where after construction was completed, we saw the gas usage ticking up. And there was quite a bit of back and forth between us and the building owner trying to dial in that demand controller to figure out why it's increasing the gas usage. Well, it ended up actually being a leak in the distribution system. So once that leak was repaired, we were actually seeing savings that we anticipated at the property, which was great. Property number 3, very similar to property number 1, 78 units with 1 central domestic hot water heating plant and 1 recirculation pump. However, there were multiple risers at this property. And this project, we were best able to disaggregate the savings from other measures because there was only 1 central washing machine upgrade included in the scope that affected the common area gas usage. So this property, we are fairly confident that the demand controller is the main energy saver for the common area gas. Now, as you can see, the savings again are not as anticipated, and we're almost not seeing any savings at this property. Moving on to project number 4, this was the first variable speed recirculation pump project. It was 148 units. One thing to note, although it was a large property, there were 10 individual buildings with each with their own recirculation system. So those buildings ranged from 5 to 30 units. However, they were all on the smaller side. And the scope of work was very similar to the other projects, low flow shower heads and aerators, pipe installation, and variable speed recirculation pumps. Now, for this project, we were actually able to see that the predicted gas usage matched the actual gas usage, which is really great, which is something that we weren't able to see in all the projects, in all of the demand controller projects. Here we are at property number 5. This is the final property. One quick note on this property, it was the only property that was master metered. So we were unable to disaggregate the gas usage from just to show the common area gas usage. However, the only measure that affected gas usage at the property besides the variable speed recirculation pump was attic insulation. 17 units had gas heating, so you were also seeing the effect or the savings from adding attic insulation to those 17 units. Now, this property was close to what we anticipated, but it's still underperforming slightly. It's a medium-sized distribution system. There are 2 hot water plants, each serving around 33 units. So why are we seeing a discrepancy in savings? Well, there's the obvious issues like project number 2, where there was a leak, underground piping, uninsulated piping, really anything that leads to high conductive losses in the distribution system can result in demand controllers or variable speed recirculation pumps being overridden. And so we end up not seeing the savings that we anticipated. But in this presentation, we're going to be focusing more on hidden issues in a domestic hot water system, more specifically domestic hot water imbalance and domestic hot water crossover. So starting with imbalance, we see the figure on the top right. When you have a larger distribution system and you have multiple risers, water wants to flow in the direction of least resistance. So the smallest loop is going to have the higher temperatures and higher flow rates, and it's going to basically short cycle the system. Now, for this loop, because it's so far away, it's going to have lower flow rates and lower temperatures. With crossover, you have cold water leaking into the hot water line. This occurs at plumbing cross connections, and more specifically, it's more commonly occurs at single handle shower valves with failed mixing cartridges inside of them. So when you have the cold water leaking into the hot water line, that cold water joins the distribution. It can mix with the hot water. It can create cold water slugs, and effectively it affects the tenant's ability to get hot water. Their water is going to fluctuate in temperature, that sort of thing. Finally, if we add controls to a building that has one of these issues or both of these issues, and more specifically a control strategy that turns off the pump, you'll see that these issues will be exacerbated, and the control strategy will effectively make these issues worse. So if you imagine in the imbalance scenario, if you had a pump that was turned off, in that furthest loop, you're gonna actually see those temperatures fall to below that 95°F temp even further. And since the GPM is so low, it's going to take even longer for it to reheat. Now, in some cases, we see it never actually getting back up to temp. So this would lead to people overriding the demand controller or the demand controller settings. Moving on to crossover. So similarly, if you shut off a pump and a property is experiencing crossover, typically you see cold water leaking into the hot water line because the cold water is of a higher pressure. Now, when you turn on that pump, you're going to increase the differential in pressure between the hot line and the cold line. So you're going to increase the amount of water that is intruding or the amount of cold water that is intruding into the hot water line. Now, quickly on imbalance repairs, one of the best ways to repair imbalance is by installing thermostatic balancing valves on the riser returns before it connects to the common return. Thermostatic balancing valves, you're able to set these at a certain temperature, and it's going to constrict flow based off that temperature. And essentially, it allows you to have a uniform temperature profile throughout all of the risers at the property. Now, crossover repairs are a little bit less intuitive. Sometimes, it really takes a lot of time to investigate the building and determine where the crossover is occurring. Now, I mentioned it's typical that it happens at single-handle shower valves. So the gentleman on the left is installing one-way flow check valves on the pipes leading to the shower. This doesn't fix the crossing over at the shower valve, but it does eliminate the chance of that cold water leaking up that hot water line and joining that distribution. A more common, stepping back to that, to those check valves, it's fairly rare that we're able to actually access those areas. And if we are able to access those areas, you also want to be able to make sure that you can access them again to maintain those check valves. Sometimes they get stuck open and they require some maintenance. So you want to be able to have those have access panels to those. A more common repair, because you don't always have access to those pipes, are just replacement cartridges. So here we have a 1225 Moen cartridge. It's a direct replacement for the 1200 Moen cartridge, which is a fairly common shower cartridge that is susceptible to crossover. We also have a no-mix shower cartridge, which is a direct replacement for mix-it shower cartridges, which are susceptible to crossover, and as well as the Moen 1200 cartridge. And on the right, we have, this is a fairly rare situation, but it does happen. We were at this property and we went into almost every unit, and every unit had two-handle shower valves, which are less likely to have crossover. And so we were fairly stumped until we went into the laundry room and we saw this pipe connecting a laundry hookup where the plumber or whoever removed the laundry machine had both of these valves were broken. One was hot, one was cold, and they're broken, stuck open. And so instead of fixing those valves, they ended up connecting the two together. And they were just, cold water was just constantly leaking into the hot water line. And this was at the start of the distribution system. So once we actually repaired this, there was no more crossover at the property. So here we have a graph showing in red supply temperatures and orange return temperatures of a central domestic hot water system. Now, this property was actually the property that installed the check valves from the photo on the previous slide. And the black line indicates when those check valve installations were complete. So as you can see, before the check valves were installed, the orange, the return temperature was fluctuating quite a bit, and we're seeing a large difference in supply temperature and return. If you think back to that variable speed recirculation pump control strategy, we want to set that to 20 degrees difference between the supply temperature and the return temperature. And if we had installed this at this property, we wouldn't see any savings because that pump would be running 24/7, just trying to keep that set point temp, because we're already seeing a difference in temperature of 10 to 20 degrees. And as you can see, after the check valve installation, we were able to get much more uniform temperatures. Now, one quick note on this property was this project actually went ahead and replaced an existing gas boiler with a central heat pump water heater. One thing to note about central heat pump water heaters is because they have slower recovery rates than gas water heaters, you want to make sure that any distribution issues like imbalance or crossover are fixed before doing that installation, because they're unable to mask these hidden distribution issues to the same extent as a gas water heater. Finally, conclusions. It should be standard practice to include crossover and imbalance investigation and repairs when you're working on installing recirculation controls or central heat pump water heaters in buildings. For new construction, looking at reverse returns, that will allow you to eliminate any potential balancing issues, and then also installing thermostatic balancing valves at the riser returns also allows you to eliminate any potential imbalance in the future. And then also you can install check valves at the showers in order to avoid crossover in the future, but also some fixtures have integrated check valves within them. Also with kitchen faucets and bathroom faucets as well. So installing those fixtures with integrated check valves is also an option to avoid crossover issues in the future. And then finally, when you have a property that may have some crossover or may have some imbalance, but it's not very significant, you can still install a variable speed recirculation pump because the savings are going to be more resilient to existing domestic hot water distribution issues. But my recommendation is if you are planning to install any sort of recirculation pump control strategy, you would want to make sure that you fix these crossover issues or these imbalance issues to make sure that you're getting the savings that you were projecting. All right, thank you very much.
Thank you so much, Jack. Just so everyone knows, we are using the QA field for questions. Please put the speaker's name first so that we know who to talk to. We are running a little bit long, so please note that there's a Zoom after meeting link for you to click so that we can get all your questions in if we don't get to them by the end of the presentation. Now we're going to hear from Amin Daga and Dr. Yanda Zhang on lab testing of CEC three-story, California Energy Commission three-story prototype multifamily hot water recirculation systems with various values and controls. Amin is a senior and mechanical engineer at Pacific Gas and Electric Company's Applied Technology Services organization. The Performance Testing and Analysis Group conducts lab research primarily to support the PG&E Codes and Standards program. Amin has been involved in lab and field hot water systems research for 12 years. Dr. Yanda Zhang is the principal of ZYD Energy, Inc., which provides energy efficiency consulting services and optimization control technologies for water heating systems. In the last 15 years, Dr. Zhang has involved in multiple aspects of energy efficient efforts, including building energy science research, emerging technology assessment, codes and standards development, program evaluation, and policy analysis. He led a team at the California Energy Commission to conduct field performance assessments in more than 30 multifamily buildings and revealed recirculation systems were really wasteful. Amen. He later helped to develop California Title 24 building standard and has conducted and is currently involved in several other water studies related to distribution systems and heat pump water heater applications. Please, Amin and Dr. Yanda, please take it over.
Thank you, Lois. So this presentation is going to look at what we learned from check valves and mixing valves in the laboratory as we were testing centralized heat pumps in a hot water system that really mimics multifamily buildings. This presentation, actually, one second. Our client is the statewide codes and standards utility program. They work with the California Energy Commission to develop new building codes and appliance standards. This project is mainly focused on improving Title 24 building energy efficiency standards and will inform the 2022 Energy Code. The efforts to improve the way that heat pump water heaters are treated in the software is a collaboration that's funded between Southern California Edison and PG&E. So before we dive into the discussion of valves, here's some background on the heat pump application testing that is currently underway. So the project technical leads are Colin Grist and Paul Kintner at Ecotope, and also Ben Larson with Larson Energy Research. So in this testing that we're doing now, we're running 24-hour hot water system tests using small, medium, and large water draw profiles. And we're trying to see how the system performs in various configurations. So thus far, we have completed testing on 4 and 8 unit apartment prototypes that we're testing in the laboratory. And later, we're going to be looking at testing commercial heat pumps in a 44-unit building. So to the picture on the right, you can see a split heat pump system where the heat pump is placed in the outdoor room, and the storage tank distribution system and draw stations that mimic apartment water use are placed in the indoor test chamber. And in the red oval is where you see the placement of the mixing valve in this system that's mixing cold and hot water to get you 120 degrees outlet temperature, which is the set point we use for our testing. And the check valve in the cyan is shown close to the heat pump. It's there to protect the heat pump and the water pump inside the heat pump that's flowing water through into the storage tank. So let's just start there with the check valves. We really looked at swing check valves. They're the default valve that's used. It was what our plumbing team installed initially in this system. They're really low cost and widely available, and they have a very low cracking pressure, which is definitely important in reducing pressure loss in the overall system. In the first graphic to the right, you can see the flapper in the swing check valve swings off its seat to allow forward flow and then swings back onto its seat when the flow is stopped. In the picture to the right of that, you can see that when the valve is in a level position, there's a small gap. So the flapper is not totally seated. And this gap is literally an open indentation for weak but persistent pressure differentials by water by water temperature differences in the system. And it can create reverse flow. And we'll get a little bit more into that in a second. But an alternative is spring check valves. They use the spring actually provides a positive seal for greater backflow prevention. And it also, spring check valves minimize the effect of water hammer. So they're definitely a good alternative. The drawbacks are that you usually need to order these, and they require specification of the spring cracking pressure. So in the laboratory, we were having issues with these swing check valves. the swing check valves did not stop the reverse thermosiphoning when the heat pump, which is the heat source, was not operating, and thereby was acting as a heat sink. Thus, hot water from the top of the tank started to, in a slow but consistent reverse flow path, flow backwards through the heat pump, which also causes additional heat losses in the system. More importantly, this persistent reverse flow caused the heat pump's internal pump to not activate during the compressor startup sequence. So we're having problems running our tests as this persistent flow was causing, our heat pumps did not turn on, and these are 24-hour long tests. And so it did actually cause a testing issue, but this can definitely occur in the field in an apartment building. So the way that we solved this was to install spring check valves with a 0.5 psi cracking pressure, and it solved this problem. So, switching from this conversation of check valves to mixing valves, you might be asking, why are we using mixing valves in these small multifamily buildings? Well, this is because heat pump-based hot water systems generate and store water at really high temperatures, and they rely on temperature stratification in the tank for the operation of the heat pump, as well as to maintain high COPs and to maximize the energy storage in the tank. Thereby, the mixing valves are necessary to reduce the storage tank outlet temperature to 120 to minimize the scalding risk, and also to deliver a comfortable, shower temperatures. So there are 3 types of mixing valves in bold that we have tested thus far for these 4 and 8 unit apartment buildings. They include the Lawler valve, the Honeywell mechanical mixer, and also the Leonard electronic mixing valve. So I'm going to go through a few plots here that kind of show the operation of these different valves. We had problems with this Lawler mechanical valve. In the left, the y-axis, we're plotting the temperature, and in the upper half of the plot, and in the right y-axis, we're plotting the water flow rate, which coincides with the lower half of the plot. So in this case, the set point on the mixing valve is set at 122, which you see in the brown line, and the recirculation system is operating at 2 GPM, which you see in the purple line below. The hot water gets to the mixing valve from the storage tank at roughly 128 degrees, which you see in the top red line. When large water draws occur, the orange arrow below shows that we're flowing 4 GPM. At this high flow rate, this mixing valve really can't adjust. It really, the outlet temperature drops from roughly 115 down to 85, and it slowly recovers after the draw has completed back to the 122 degrees. Ultimately, this apartment doesn't see consistent temperatures or high temperatures for the duration of these draws. And this sample testing that we did, we realized that we can't use this mixing valve and maintain 120 degrees throughout for our tests, the application testing we're going to do. And moving forward, ultimately, what we found out was really these types of thermostatic mixing valves are best suited for large office buildings that have continuous high recirc flow rates, that have relatively large volume distribution systems, and low draw volumes and draw times. So therefore, they're really relying on the distribution system to kind of really moderate the temperatures that are getting to, say, hand sinks. And they're not designed, at least from the experience we learned in the laboratory, for the much higher flows we see in multifamily buildings. So moving to the Honeywell mixing valve, this is actually serviceable with all types of distribution systems with and without pumps or controls. In the top plot, we are flowing 2 GPM continuously in the purple line. And what we see is that we've set this at 120 degrees during the continuous recirc only phase. And when there's draws, say a 2 GPM draw or a 4 GPM draw, we see a temperature drop. So it delivers water at below 120. There might be a 4-degree drop if we have a 2 GPM draw, or even a 9-degree drop. But it's very consistent for the draw period, and then it recovers. And so that's maybe a limitation of the traditional mixing valve, which is that it can't continuously provide 120-degree set point just during the recirculation and maintain that when there's draws. There's going to always be a drop-off. And so in the lower chart, we are using demand control pump with a 20-minute auto prime, and we've set it at 122 degrees. So it's a little trade-off, a little bit higher set point when the recirculation is bringing hot water throughout the system. But then when there's draws, it will drop the set point. It will drop the outlet temperature, but not significantly. And so what we found out is ultimately this type of valve is serviceable. It works with different applications, and it's also very low cost. So it is very feasible for buildings to use this type of valve. Moving on to the Leonard mixing valve. This is a digital mixing valve, and it does fine even at very low recirc flow rates, but it does struggle with continuous recirculation systems, with demand control systems. And so I know I'm short on time, so I'm just going to quickly go through to the final slide. And ultimately, what we saw is that proper specification of valves have an oversized impact on system performance. And we put together this slide right here, or this table right here, that compares the electronic and thermostatic mixing valves of various types of recirculation. And what we saw is that electronic mixing valves work really good with continuous recirculation, but are currently not set up well to work with no recirculation or with any kind of long duration pump controls. This particular valve just turns off. It just doesn't, it's not able to mix after a certain time period and has to be reset. The thermostatic mixing valve, the Honeywell valve, worked really good. It was serviceable for everything, but it also, it struggled at low flow rates. And, to conclude, we've studied a little bit check valves and mixing valves, but there's another type of valve, balancing valves, that's also really important for us to look at. And they're used in mid to high rise apartment buildings. And the work that we'll be doing next is on distribution systems, riser distribution systems, and Yanda is going to get into that right after this. So some recommendations we have is that, we need to do a larger test of mixing valves and really develop a lab test criteria, which could down the line lead to developing a qualified product list. There's just lots of different ones out there, and it's worth to really understand them better and see what's suited for this application. Kind of moving to the residential side, GE has integrated this electronic mixing valve in a heater, and that's something which should also be looked at. This idea that you could have a very compact mixing valve that can maybe work for all these different recirculation applications could be a really great approach. There was an earlier presentation by Greg Poffenhauer that looked at using mixing valves, and they really did a good job in maintaining capacity in these residential heat pump water heaters in the wintertime. And it reduced the resistance heating that was needed to get through, at those, very intense times in the winter where you need to increase the temperature significantly. And so,
Amin, I'm going to jump in here. We only have 5 minutes left for the session, so we better let Dr. Zhang get on.
Sorry, Yanda. Take it away.
No problem. I think I'm fine. I think Peter, Jack, and you have set things up, talked a lot of related issues, and I don't have to repeat them, so my presentation can be brief. And also, the presentation I'm providing is relating a study that we are in the process to conduct. So we don't have any actual data to show you. It's more about to present the approach and the idea to you to get your feedback. So I'm okay. We probably don't need that much time. So the project we have here is trying to say how do we test 3-story recirculation system in a lab? That's the problem. And why are we doing that? Peter explained already that recirculation is really massive and they're really wasteful, has a lot of pipe and leads to a lot of heat loss. And previous study suggested about 1/3 of the energy input into the water heating system can be just used for sustain the recirculation system, right? 1/3, a lot. How do we reduce that? Better design. Peter discussed one of the options, to significantly reduce the pipe size, reduce pipe surface area, reduce heat loss. Good insulation always is a good solution. And then once you have a system in place, is how you control the system could make a difference. And Jack explained some of the issues that he identified. I concur. That we saw the same issue. It's related to the imbalance. It's related to the crossover flows. On top of that, now we have the kind of the need to moving towards using heat pump water heaters. Then the return temperature from the recirculation is also very important. So this is all leads us to have a better understanding of how the recirculation system actually works. I mean, in details, how the delivery temperature to individual units is going to be affected by the recirculation flow and control and kind of the imbalancing issues. Those are the issues that are very hard to study in field because the pipes to individual units, they're really just not accessible, right? So they're inside the walls. And also, under the site operation condition, you just don't have much control what you can change because, tenants need to have a good, basically have their individual schedules. You can't mess around with. In the lab, you would have much more flexibility, right, to change flow conditions, temperature conditions, to understand how system responds to controls, to response different configurations of, balancing valve configurations. So that's what we're going to do. So how we're going to do it? So the general approach is that, yes, we're actually going to use a actual size recirculation system. But obviously, we're not going to build a 3-story apartment. So what we do is basically kind of fold the pipe runs into a much tighter space. So this is the actual design of the testing system. It's still pretty large, but definitely not anywhere close to a 3-story building. And what you see is that we have supply pipes, 3-inch kind of at the bottom, representing kind of the first floor ceiling of a building. And then you have, coming up, you have the risers going up to the third story ceiling and going back to the return. And another picture shows slightly better view because we remove the frame, right? So you can see the supply. And how do we fold it? You can see the kind of the zigzag of supply pipes instead of making a straight 160 feet long. So we kind of banded it so that it can fit into a small space. And this is a better view of how the pipe runs. We kind of arrange it so that they don't on top of each other to have interference. This way, they're a little bit more separated. So when we do have the system set up, we're working on it. We can test the system under kind of various conditions. For example, right, we can vary the flow rate, so recirculating flow rate, for example, and we can try to see at what minimum flow rate, what's the minimum flow rate you can have such that you can still have satisfactory hot water delivery, right? The temperature is not going to be too cold to the last one along the recirculation system. And we can also change, change different, use different balancing valves to test how they can help to improve the flow balancing. And then we will also try different control strategies and under different draw schedules. This will lead to a lot of test conditions. We're not going to be able to test all the different combinations. Rather, we'll adjust them according to our test result. So, before we conduct the test, we did perform some simulation analysis so that we can have a better understanding what are the more important issues we can focus on. And this one, for example, shows you how the temperature changes along the distribution system from the supply to the return at different locations, different like riser locations, and with different recirculation flow rate. For example, you will see, if you're going to use a low recirculation flow, just say 1 GPM, you won't be able to, make sure that hot water is kind of like the water temperature is adequate at certain riser locations. Some part of them will be get cold water. And this is a more additional analysis to simulate what if we can have a pump control, turn off pump. How would that affect temperatures along different locations throughout the recirculation? So that said, we don't have data, actual measurement data to show you, right? But we hope that we provide enough information to let you know this is something we're doing. We would love to get feedbacks from you to see what else we need to consider. What are the kind of the additional issues we should look at. Thanks. Then here's my contact. Please let us know if any questions and inputs.
Thank you so much. Thank you. Since we are over, we're at 3:03 right now. We're going to jump to the Zoom room and we'll address questions. Right. Thank you, everybody.
Thanks. Where's the Zoom button?
Kim, can you point to the Zoom button? I don't see one on my screen.